His mathematical journey began since he has graduated from CMI with an honors degree in mathematics and computer science in the year 2013, followed by a master's degree in mathematics from RKMRC, Belur in the year 2015. He then received his PhD in mathematics from Harish Chandra Research Institute under the supervision of Professor R. Thangadhurai in the year 2020. And he has completed his institute postdoctoral degree in mathematics under the mentorship of Professor Anupam Saikia in 2020 to 21 and NPHM postdoctoral degree in 2021 to 23 at IIT Guwahati. In terms of research, he is primarily interested in number theory. Particularly, it includes the ideal class groups of algebraic number fields, Polya groups, number field with large Polya groups, integer valued polynomials, and arithmetic of elliptic curves, in which he has published several papers. He has achieved the Inspire Scholarship from 2010 to 2015 and has also received Harish Chandra Memorial Award in 2018. So without any further delay, I request you, sir, to begin today's seminar.
So am I audible?
Yes.
Thank you. So thank you very much for the warm introduction, and I am very happy to be here on the invitation by Bhargav Maharaj. In fact, I had delivered a lecture a few months back, probably in the month of September, and I am very much delighted to see your enthusiasm to organize such a beautiful fest. So, without further ado, let me begin. My lecture, which is Euclidean type proofs of infinitude of primes in some arithmetic progressions. So prime numbers are something that we are all familiar with. These are the so-called the building blocks of integers. So what do we mean by building blocks? That means if we know the prime numbers, in some sense we know all the integers. That is captured by this fundamental theorem of arithmetic. This states that if we take any positive integer which is bigger than 1, then it can be uniquely expressed as a product of prime numbers. So unique means we do not differentiate between the order of the prime factors in which we are expressing the number. For example, if we take 12, we write it as 2 squared times 3 or 2 times 3 times 2. So we do not distinguish between these two representations. So if we know the prime numbers and we keep multiplying prime numbers with themselves, then we end up having all the positive integers. So the natural question is, how many prime numbers are there? So in other words, whenever we come across some set, the first question that we should ask in order to understand that set is whether that set is finite or infinite to begin with. So about 2000 years ago, Euclid proved that there are indeed infinitely many prime numbers. So if we keep on listing the prime numbers 2, 3, 5, 7, 11, 13 and so on, this list never ends. And he gave a truly elegant proof of this theorem, which goes as follows, and most of you are already familiar with this proof, but anyway, let me just recall the proof. So the proof goes essentially by the method of contradiction. So if we assume that the set of primes is finite, we are going to arrive at some contradiction which will prove that the prime numbers are infinite in number. So if the set of prime numbers which are denoted by p, if that is finite, let the elements of the set P be P1, P2 up to Pk. So now the ingenious construction done by Euclid says that if we consider the number P1 times P2 times up to Pk plus 1, then the fundamental theorem of arithmetic tells us, since this integer is strictly bigger than 1, either this number itself is a prime or it is a product of prime numbers. So if this number itself is a prime, then certainly it is different from all the PIs that I had listed earlier. If not, then it will have a prime factor which is also different from all these PIs, because if some prime number, some prime divisor of n is there, then it has to come from P1, P2, Pk if that list is finite. But any PI that is already making its appearance in the product P1, P2, Pk. So if it again divides n, that means it has to divide n minus product of P1, P2, Pk, which is 1. But no prime number can divide 1. Therefore, this gives us a desired contradiction, which proves that the set of prime numbers is infinite. Now, there is a mistake most of us often make, that it seems that the integer Euclid constructed that itself is a prime, but that's false. So for example, if we take the first few prime numbers, if you take just 2 and 2 plus 1, that turns out to be a prime. If you take 2 into 3 plus 1, again that's a prime. Similarly, 2 into 3 into 5 plus 1, that is 31, that is again a prime. So after working with some small numbers, we might be under this false assumption or notion that probably if we multiply out first few prime numbers and add 1, probably the resulting number is also prime. But that's not true in general. For example, if you multiply all the prime numbers from 2 to 13 and then add 1, then this is a composite number, which is the product of 59 and 509. So we can also see that clearly we are missing out many primes. For example, we are not getting 17 or 19 these prime numbers, but we end up having two new prime numbers, namely 59 and 509. But Euclid's algorithm, it doesn't actually tell us how to find the next prime. It only tells us that if we start with a finite set of prime numbers, we also end up having a new prime number, which in this example are given by 59 and 509. Let us also see another proof by Euler. Euler also gave a different proof of infinitude of primes, which is given as follows. So the trick is said, first if you assume that if the set of prime numbers P is finite, then we are going to have some equation, and from there we want to derive some contradiction. So for any prime number P and real number S, we see that 1 plus 1 over P power S plus 1 over P power 2S up to this infinite sum. So this is the geometric progression. So this sum is equal to 1 over 1 minus P to the minus S. And the fundamental theorem of arithmetic tells that any integer greater than 1 is the product of prime numbers in an essentially unique way. So if you take the set of all prime numbers and take 1 by 1 minus P to the minus S and expand it out, you should be getting 1 by n to the power S for every natural number n. For example, if you just take P to be 2 and 3 and you take the geometric series 1 plus 2 plus 1 by 2 square plus 1 by 2 cube and so on, and the multiply it with 1 plus 1 over 3 plus 1 over 3 square and so on. So if you expand it out, you will get all the numbers of the form from 1 by 2 power something times 3 power something. So similarly, if you allow all the prime numbers, then you will get summation 1 over n to the power s, where n varies over all the integers. Now if the set of prime numbers is finite, then as s approaches to 1 from the right, the left hand side is finite because there are only finitely many terms, and each term is convergent as s tends to 1. But we know that the right hand side tends to summation 1 over n, which is a harmonic series, and all of us know that this is a divergent series. So if this equality has to hold and the set of prime numbers P is finite, then we get the left hand side to be convergent, whereas the right hand side to be divergent, which cannot be true. Therefore the set of prime number has to be infinite. Now the point is, if we have such an elegant proof of infinitude of primes due to Euclid, why do we need to care about this proof of Euler? So let us look at the primes of the form 4k plus 3. So if we want to prove the infinitude of primes of the form 4k plus 3, let us try to adapt the method of Euclid. So by the sake of contradiction, we assume that there are only finitely many primes, say P1, P2, Pr of the form 4k plus 3. Then Euclid's technique is to cook up a new natural number from which we can hope to derive some sort of a contradiction. So in this case, if you take the product P1, P2, Pr plus 1 or plus 3, something like that, probably it is not going to work. But if we make a little tweak to that number, say if we take this number 4 times P1, P2, Pr minus 1, then it is going to work. Why? Because first note that the capital N, that integer, that is indeed of the form 4k plus 3. Therefore, if n is itself a prime number, then again we get a new prime and we are done. And if it is not a prime number, then it must have a prime divisor of the form 4k plus 3. Why? Because any odd number is made up of primes, and primes are either of the form 4k plus 1 or 4k plus 3. If all the prime factors are of the form 4k plus 1, then certainly the product of finitely many numbers of the form 4k plus 1 is again of the form 4k plus 1. But the number n is of the form 4k plus 3. Therefore, it must at least have one prime factor of the form 4k plus 3. And this prime number is a new prime number which is not listed in the above list P1, P2, Pr. Therefore, we get a new prime number, and hence the set of all prime numbers of the form 4k plus 3, that is infinite. Now what happens if we try to adapt the same technique to prove the infinitude of primes of the form 4k plus 1? So let us try to see how far Euclid's method enables us to conclude something along that direction. So again, if we assume that there are finitely many primes, say P1, P2, Pr of the form 4k plus 1, so the question that comes to our mind is, what should be our choice of capital N in this case? Earlier it was 4 times P1, P2, Pr minus 1. So along that line, our first thought should be, let's take just 4 into P1, P2, Pr plus 1. So that the number that we are having, that is again congruent to 1 modulo 4. But the question is, will that work? The obvious difficulty is that if you take two prime numbers of the form 4k plus 3, the resulting number is of the form 4k plus 1. So it may happen that the integer capital N that we cooked up here is made up of an even number of primes, all of the form 4k plus 3. Then there is no contradiction. So here it tells us that we need to change our capital N a little bit. So just to substantiate the concern raised in this boxed form, if we take just 5, so our capital N is 4 into 5 plus 1, which is 21, which is made up of 2 primes 3 and 7, both of which are of the form 4k plus 3. So we do not get any prime factor of the form 4k plus 1. Similarly, if you take 5 and 17, so 4 times 5 into 17 plus 1, which is 341, is again a product of 11 and 31, neither of which is of the form 4k plus 1. So this choice of capital N is not going to give us a proof. So the point is, how do we change this capital N? So at this point, we need to make a little bit digression from primes to quadratic residue and quadratic reciprocity, and I will show you in a moment how those notions are related to the infinitude of primes of this form. So if we fix an odd prime number p and we consider an integer a which is relatively prime with p, the definition of a quadratic residue modulo p is that if the integer is a square modulo p. For example, let's say you take 2 and then 3 square is 9, which is congruent to 2 modulo 7. So even though 2 is not genuine square integer, 2 is the square modulo 7. So if the congruence x square congruent to a modulo p has a solution, then we say that the integer a is a quadratic residue modulo p. And just to capture the notion of quadratic residue, Legendre introduced this symbol, which is by and large known as Legendre symbol. It says that if we have an odd prime number p and an integer a, then this notation a by p bracket, this is 1 if a is a quadratic residue modulo p, it is minus 1 if a is not a quadratic residue modulo p, and it is 0 if p divides a. So for example, as I said, if you take 2, then 3 square congruent to 2 modulo 7, therefore we can take x to be equal to 3. Therefore 2 is a quadratic residue modulo 7, hence the Legendre symbol 2 over 7 is 1. But if you take 2 by 5, this Legendre symbol is minus 1. If you take any integer and you square it, you are never going to get that to be congruent to 2 modulo 5. Hence the Legendre symbol is minus 1. For example, you can directly check if you take 0 to 4 and you square each of these numbers, none of which is congruent to 2 modulo 5. So we do indeed have examples of quadratic residues as well as quadratic non-residues. Now what are the properties of this Legendre symbol? There are several such properties. So some of which are, if two numbers are congruent modulo p, then either both of which are quadratic residues modulo p or both of which are quadratic non-residues modulo p. And certainly if you take any square number, a square is always congruent to a square modulo p. Hence, any square integer, the Legendre symbol of any perfect square, that is 1. And the third one is the most important one in this case. It says that the Legendre symbol a by p, that is congruent to a to the power p minus 1 by 2 modulo p. Now in view of Fermat's Little theorem, we know that a to the power p minus 1 is congruent to 1 modulo p. So if we raise it to the power p minus 1 by 2, we should get either 1 or minus 1 modulo p. So which one should it be there? It says that the Legendre symbol of a by p, that is the sign of this a to the power p minus 1 by 2 modulo p. And the last one says that this symbol is multiplicative in nature. So if you want to determine whether the product of two integers is a quadratic residue or non-residue, it is enough to look at the individual symbols a by p and b by p. So quickly, if we take a equal to minus 1, then the third property says that minus 1 by p is congruent to minus 1 to the power p minus 1 by 2. And if minus 1 by 2 is 1, if and only p is of the form 4k plus 1. So minus 1 is a square modulo p, if and only p is of the form 4k plus 1. Similarly, we can also try to find out for which prime numbers p 2 is a quadratic residue, and the proof is a little bit difficult than the quadratic residue symbol of minus 1. So I just state this. So it says that 2 is a quadratic residue modulo p if and only p is congruent to either 1 or minus 1 modulo a. So if you take, for example, p equal to 13, which is congruent to 5 modulo 13, so this theorem says that 2 should be a quadratic non-residue. If you take p equal to 17, which is 8k plus 1 form, therefore 2 is a quadratic residue modulo 17, and so on. Now the most important theorem in this field of quadratic residue, and this is quadratic reciprocity, which Gauss mentioned as a golden theorem. It says that if you take two distinct prime numbers p and q, then in some sense p is a quadratic residue modulo q if and only q is also a quadratic residue modulo p. So the only first factor is that minus 1 to the power p minus 1 over 2 times q minus 1 over 2. So from this example, we can see that if you take any of p and q to be p or q to be congruent to 1 modulo 4, then minus 1 to the power p minus 1 by 2 into q minus 1 by 2, that turns out to be minus 1 to the power some even integer. So that will give me 1. So in that case q by p will be equal to p by q. So let us look at one example. So this 17 over 43, this Legendre symbol if we want to compute, so that means we want to see whether 17 is a quadratic residue modulo 43 or not. That means whether the congruence x square congruent to 17 modulo 43, this has a solution or not. So the theorem of quadratic reciprocity, this law tells us that this is 43 over 17 times this minus 1 to the power 17 minus 1 over 2 times 43 minus 1 over 2. And 17 minus 1 over 2, since 17 is the prime of the form 4k plus 1, that doesn't contribute anything. So 17 by 43 Legendre symbol is equal to the Legendre symbol of 43 over 17. And 43 and 9 are congruent modulo 17. Therefore the Legendre symbol is equal to 19 by 7, 9 by 17. And 9 is itself a square, therefore this is 1. So we conclude in a nutshell that 17 is indeed a quadratic residue modulo 43. So now, how do we use this information to prove the infinitude of primes of the form 4k plus 1? So let us come back to the story that where we left. So now, again we are assuming that if possible, let P1, P2 and PR be all the primes of the form 4k plus 1. So earlier we had seen that n equal to 4 into P1, P2, PR plus 1 doesn't work. But instead, if we take this integer 2 P1, P2, PR whole square plus 1, this is going to work. Why? Because in this case, first note that n is congruent to 1 modulo 4. Again, if n is itself a prime number, then we are done. If not, then we choose a prime divisor P of n. Fundamental theorem of arithmetic guarantees such a prime exists. So if we work modulo P, since P is a divisor of n, that means n is congruent to 0 modulo P, right? So that means minus 1 is congruent to 2 P1, P2, PR whole square modulo P. In other words, minus 1 is a quadratic residue modulo P. And we had observed that minus 1 is a quadratic residue modulo P if and only if P is of the form 4k plus 1. So that means here we get this prime P we are working with, that turns out to be a prime of the form 4k plus 1. And this is different from all the primes P1, P2, PR. So in this case also we could produce one new prime. So the list of primes of the form 4k plus 1, that is infinite. So now the question is, what about we change the arithmetic progression? So 4k plus 1 and 4k plus 3, these types of numbers are two separate arithmetic progressions. What if we take any other arithmetic progression? For example, if we take P congruent to 1 or 3 or 5 or 7 modulo 8, you might be wondering that why we are not considering P congruent to 2, 4, 6, because P congruent to 2 or 4 or 6 modulo 8, they consist of even integers. So we cannot get any prime numbers apart from 2. So there is no question of having infinitely many primes. But if we take instead these numbers, P congruent to 1 or 3 or 5 or 7 modulo 8, there is a chance that we could have infinitely many primes in each of these cases. So let us first try to prove the infinitude in the case of P congruent to 7 modulo 8. So here I am not repeating the same kind of arguments. In each case, let me just point out what should be our choice for capital N. So the choice of capital N we are taking here is P1, P2, PR whole square minus 2. Then this is a number which is odd, and if P is a prime divisor, then N congruent to 0 modulo P tells us that 2 should be congruent to P1, P2, PR whole square modulo P. That means 2 is a quadratic residue modulo P. And we have seen that 2 is a quadratic residue modulo P if and only if P is either 1 or minus 1 modulo 8. So if all the prime divisors are of the form 1 modulo 8, so is their product, but this number is not congruent to 1 modulo 8 because each of these numbers P1, P2, PR is odd. So they are square if you take, each of these is congruent to 1 modulo 8. So P1, P2, PR whole square is congruent to 1 modulo 8. 1 minus 2 is minus 1, therefore that is a number which is congruent to 7 modulo 8. So any number of the form 7 modulo 8 cannot have all its divisors of the form 1 modulo 8. So in this case also, n must have a prime factor which is congruent to 7 modulo 8. So this case also we can prove that there are indeed infinitely many primes of the form 8k plus 7. Then what about 8k plus 5? In this case, this is our choice of n. So again, we can use the fact that if p is a prime divisor of n, then minus 1 turns out to be a quadratic residue, and minus 1 is a quadratic residue if and only if p is 1 modulo 4. So if we try to read a number which is 1 modulo 4, in which congruence class does it lie when we consider it in the congruent modulo 8, it turns out that it can be either 1 modulo 8 or 5 modulo 8. So again, if all the divisors are of the form hk plus 1, so is their product, so it cannot be possible, therefore it must have a prime factor which is congruent to 5 modulo 8. So we could so far prove that there are infinitely many primes which are congruent to 7 modulo 8, there are infinitely many primes which are congruent to 5 modulo 8. Similarly for hk plus 3, this choice of n will work. So by now you are kind of, you can see that what are the techniques that I am going to employ here. Again, I am going to use when minus 2 by p is going to be 1, and minus 2 by p can be evaluated as minus 1 by p times 2 by p, and by looking at all the cases, we boil down to the case of only p to be 1 or 3 modulo 8. Then the same reasoning finishes the proof. Now comes the trickier part of the primes of the form hk plus 1. So remember, in case of 4k plus 1, we had to face a little bit of difficulty that prompted us to go beyond Euclid's method and look for some other things. Here also, the direct use of quadratic residue and those theorems are not of that much use to us. But instead, if we take this number 2 times p1 p2 pr power 4, instead of squaring, this time we are taking power 4 plus 1, then what happens? Then this number 2 p1 p2 pr power 4 is congruent to minus 1 modulo p. So if we square it again, we will get that 2 p1 p2 pr whole power 8, that is congruent to 1 modulo p. That means in the multiplicative group z mod pz star, this element 2 p1 p2 pr, it has order 8. Now, if we have a group of order p minus 1, where we have found one element of order 8, what does Lagrange's theorem tell us? It tells us that it should have, its order should be divisible by the order of an element, which is 8. That means the order of the multiplicative group z mod pz star, that is divisible by 8. That means p minus 1 is divisible by 8. That is, p is congruent to 1 modulo 8. So in this case also, we could find a new prime p which is congruent to 1 modulo 8. So the question that comes to our mind now is that there are infinitely many possibilities for p congruent to something modulo something. It is not humanly possible to fix two integers a and m and check whether p congruent to a modulo m, there are infinitely many primes or not, by employing some techniques of quadratic residue and all. So how can we generalize this? So that means if we take any arithmetic progression, because p congruent to a modulo m is nothing but an arithmetic progression whose first term is a and common difference is n. So any arithmetic progression starts with some integer a. So we are talking about arithmetic progressions in integers and some common difference d. So for example, the set of all natural numbers is also an arithmetic progression whose first term is 1 and common difference is 1. So if the GCD of the first term and common difference is strictly bigger than 1, then we cannot hope for getting infinitely many primes, because each of these numbers a plus d, a plus 2d, that is divisible by the GCD which is bigger than 1. For example, if you take all the multiples of 3, 6, 9, 12, only one number is prime, namely 3. Every other integer is divisible by 3 and therefore cannot be prime. So we need to assume that GCD of the first term and the common difference is 1. So if we have the GCD of first term and common difference to be 1, then their is a chance that we might be having infinitely many primes in that arithmetic progression. So the question is, do we always have infinitely many primes? And the answer is yes, and that is proved by Dirichlet around 1837. So you just notice the difference of time frames. Around 2000 years ago, Euclid proved that there are infinitely many prime numbers. And in 1837, Dirichlet could prove that there are infinitely many primes in any arithmetic progression whose first prime and common difference are co-prime. So why did it take so much time? So that means probably Euclid's method is not sufficient to yield a proof of Dirichlet's theorem for any arithmetic progression, right? But we have seen examples of arithmetic progressions like 4k plus 1 or 4k plus 3 or 8k plus 1, 3, 5 or 7 modularly, for which Euclid's method can be twisted a little bit to yield a proof. But since Dirichlet proved it using a different method altogether, using some very sophisticated techniques from analytic number theory, using L functions and all, so that means probably somewhere something in Euclid's proof lacks. That's why we cannot generalize it to its fullest extent. So the question is, how far can we push the idea of Euclid to obtain proofs of infinitude of primes in some arithmetic progression? So what are the arithmetic progressions for which Euclid's method can be extended? So for this, we need to introduce the notion of an Euclidean polynomial. So let us take a hint from the examples that we have seen so far. So in the proofs, let's say for 4k plus 1 or 4k plus 3 type of primes, essentially what we did, we cooked up two integers of some particular form. For the first one it was 4x minus 1 type, and for the second one it was 4x squared plus 1. And what are the properties of these two polynomials? In place of x, we plug particular values to yield certain prime divisors. So let me just rephrase it in this form, that if we start with a polynomial and look at the values at integer arguments, for example f0, f1, f2, you can take negative values as well, and look at the prime divisors of this set. So you take f1, look at the value, list all the prime divisors of f1. You then go for f2, that's an integer, because this is a polynomial with integer coefficients. It will have certain prime factors. So you look at all the values and look at all the prime divisors. So what is the property? That for certain values of n, we get a prime divisor which is coming from our desired arithmetic progression. So this prompted us to define or call a prime number p to be a prime divisor of fx if f has a root modulo p. That means fn is congruent to 0 modulo p. So said differently, if p divides fn for some n. So now we list this set of all prime factors p of the values of this polynomial f at integer arguments by p of x. So the question is whether this set is infinite or not. If this set is finite, then we cannot hope to get infinitely many primes. Luckily, this set is always infinite, whatever polynomial non-constant we start off with. So Schur proved this around 100 years ago, that if we start with any non-constant polynomial f with coefficients in z, then the set of prime divisors of this polynomial, that's an infinite set. And then Nagel proves that if we take two polynomials f and g, then the prime. To generalize the method of Euclid's proof, then at least we need to define what we mean by a Euclidean type proof. So the entire talk so far is kind of a motivation for us to define what should we mean by an Euclidean proof. So from these examples, this is a very reasonable choice as a definition. So we say that an Euclidean proof for the infinitude of primes in some arithmetic progression congruent to a modulo n exists, if there exists an irreducible polynomial fx such that all but finitely many elements of its prime divisors are either congruent to 1 modulo m or congruent to a modulo m. You notice that this has always been the case for all the examples that we have chosen so far. Primes of the form 4k plus 3, we had chosen the prime 4x minus 1, that was irreducible to begin with over z, and all but finitely many prime divisors are either of the form 4k plus 1 or of the form 4k plus 3. If we had chosen primes of the form 4k plus 1, then 4x squared plus 1 was our choice of polynomial. That was again irreducible to begin with and satisfied this condition. So now the question is, for which arithmetic progressions can we find or can we ensure that such a polynomial exists? So that entire quest for the search of an Euclidean type proof reduces to the search for certain type of polynomials. So that's how we make progress. That's how we reduce a question to something that we are able to tackle. So Ramamurthy in 1988, he published a paper. Actually, he published it much later than he proved it. He actually came up with the idea of this proof when he was in his bachelor's final year. And he has written a very interesting article about how he could come up with the idea of its proof. So in his 4th year of BSc, he was looking for topics for his bachelor's thesis, and roaming around in the library, he hit upon a paper which kind of inspired him to think about this problem. So what should be the arithmetic progressions for which we can have some sort of an Euclidean type proof? And he could prove that such an Euclidean proof of infinitude of primes exists if and only if a square is congruent to 1 modulo n. So you now see, if we take primes of the form 1 modulo 4 or 3 modulo 4, both 1 square and 3 square are congruent to 1 modulo 4. If we take primes of the form 1 or 3 or 5 or 7 modulo 8, 1 square, 3 square, 5 square, 7 square, each of these numbers is congruent to 1 modulo 8. So that's why we had Euclidean type of proofs for those kind of arithmetic progressions. So if we now take some other prime, let's say if we take this arithmetic progression, let's say just p congruent to 6 modulo 17, since 6 square is 36, which is not congruent to 1 modulo 17, so we will not have an Euclidean type of proof. That means Euclid's method does not enable us to have a proof for the infinitude of primes p that are congruent to 6 modulo 17. But Dirichlet's theorem asserts us that there are indeed such primes infinitely many. So I end my lecture with an example for primes p of the form 15k plus 4. So Ramamurthy's theorem tells us that this 4 square, which is 16, and that is congruent to 1 modulo 15, that means such a proof should exist. So now our quest should be, what should be the polynomial that we should start off with? And the method of the proof suggests that this is the polynomial x power 4 minus x cube plus 2x square plus x plus 1. And if we slightly rewrite it as something square plus 15x square plus 4, then we can see that for any prime divisor p in Pf, the minus 15 should be a quadratic residue modulo p, because something square plus 15 times something square is 0 modulo p. So therefore by rearranging we see that minus 15 is a square modulo p. So using the quadratic reciprocity law, we can arrive at this, that p should be either 1 or 2 or 4 or 8 modulo 15. Similarly, fx can also be expressed as minus x square plus x by 2 minus half whole square plus 3 upon 4 into x plus 1 whole square. So again, this implies that minus 3 by p is 1, and hence p should be 1 modulo 3. And again writing finally fx as something square minus 5 by 4 into x minus 1 whole square, we get that p is either 1 or 4 modulo 5. So by combining these three observations, we conclude that p is either 1 or 4 modulo 15. Therefore, we win. We have a prime factor which is congruent to either 1 or 4 modulo 15. Now the rest of the proof is easy. Just plug 15x plus 1 in place of x. Therefore, the resulting polynomial is 15 times some polynomial plus 4, which will give us an integer of the form 15k plus 4 when x is an integer, and therefore not all the prime divisors can be of the form 1 modulo 15. Therefore, it should have a prime number which is congruent to 4 modulo 15, and therefore we get indeed infinitely many such primes. So, thanks for your attention.
থ্যাংক ইউ ভেরি মাচ স্যার। এবার আমাদের প্রশ্ন উত্তরের পালা। তো যদি কারো কোনো প্রশ্ন থেকে থাকে নির্দ্বিধায় জিজ্ঞেস করতে পারো। সো যদি কারো প্রশ্ন থেকে থাকে, আই হোপ কারো নেই প্রশ্ন, আর আমরা নেক্সট এগিয়ে যাচ্ছি তথাগত।
যেহেতু কোনো প্রশ্ন আর নেই, now on behalf of everyone present here, I sincerely thank you for your illuminating lecture. It is very true that your lucid explanations and insightful perspectives have made complex ideas of number theory so accessible and engaging to all of us. Your talk has been both enriching and inspiring, encouraging us to delve deeper into the field with renewed interest. Sir, we are extremely grateful for your time and guidance. It has been an absolute privilege to hear you. Thank you, sir.
স্যারের জন্য আমাদের শ্যামদা অনিমেষ স্যাক্রেট এগেছেন। তো শ্যামদাকে রিকোয়েস্ট করবো স্যারকে যদি পোর্ট্রেটটা একটু হাতে তুলে দিত। শ্যামদা পোর্ট্রেট। We have applause please.